Today it is my pleasure to introduce somebody you may have noticed around, which is Justin Feng, a member of CENTRA. And I'm very happy that he stepped in to give a seminar today. So please, Justin, go for it.
Thanks, Alex. So I guess I'll be talking about some work that I started doing for my PhD dissertation and then left on the back burner for a while and picked up in the past 2 years. So I did give a talk on the Weiss variation here a few years back, but there have been a few developments since then, which I will tell you about in the second half of the talk. But in the first half of the talk, I'm going to do an advertisement. So so this is more of a pedagogical, I guess, well, an advertisement for the pedagogical utility of the Weiss variation. And so a lot of the results here are probably things that, or at least the results are not exactly new, but this is a new way to obtain those results. And what I will try to convince you of is that this is a faster way of getting to a lot of the results that you have learned in classical mechanics. So let's get into it. So first, what's the Weiss variation? Well, the Weiss variation, it's the variation of the action, but including boundary displacements. Now, of course, it's not just that. There is a particular repackaging of these boundary or endpoint displacements that you have to perform to get the Weiss variation, at least to get it in its most useful form. And as I mentioned, it's useful pedagogically as a unified formalism, which allows you to derive a whole bunch of results very quickly and very efficiently. And one of the reasons why I'm interested in it, at least for its applications in gravitation, is because it's useful for constructing Hamiltonians without having to perform a 3+1 split beforehand. And so it's a more covariant way of getting a Hamiltonian formulation of a given theory. And of course, for general relativity, we already have a Hamiltonian, but what I'm particularly interested in going forward are its applications in modified theories of gravity. So I guess
Who was that?
so Paul Weiss, I think, was a collaborator of Paul Dirac, and I don't know if he was a student or the postdoc of his, but he worked very closely with Paul Dirac. So anyway, I guess yeah. So it's very hard to I guess find the Weiss variation stated as such in the literature. There's really only a handful of works in the literature that refer to the Weiss variation as such. But maybe when I show it to you, when I show you the form of the Weiss variation, you'll recognize it. So so I guess maybe I'll give you an illustration of what's different about the Weiss variation. So I guess in the standard variation, what you do is you start with some path, and then you look at small displacements of the path. And so you add functions which to this original function q of t. So q is your variable, your dynamical variable, and t is your time parameter. And what you do is you add functions to this which vanish at some time t2 and some time t1, and the value of the function is held fixed under these variations. Now, with the Weiss variation, not only do you allow the values of q to vary, but you also vary the time parameter when you perform variations of the action. And so the game, or the repackaging of the boundary terms that I was referring to earlier, is to rewrite all the endpoint contributions or the boundary contributions in terms of the total changes, delta q and delta t. And so, I'll show you how it's done in the next slide. So here's the formalism. You start with an action of this form, and the variation when you include endpoint displacements, takes this form. And so this piece is just the Lagrangian evaluated at the endpoint times the amount by which you displace the time parameter at each endpoint. This curly E, that's the Euler-Lagrange operator acting on Q, and this P is the derivative of the Lagrangian with respect to the second argument. So what we do is we write out the total change in Q in terms of the variation evaluated at the endpoints, plus the time derivative at the endpoint, the original endpoint, the undisplaced endpoint, times the amount by which you displace each endpoint. And so you write the total variation, and then what you do is you solve for delta Q, the little delta Q, and you replace this delta Q in the boundary term, and this is a result. And you might recognize that the term in front of delta T just happens to be the Legendre transformation of the Lagrangian, which is, of course, the Hamiltonian. And so that is the Weiss variation. P dot delta Q, the total change in the endpoint value of your dynamical degree of freedom, and minus the Hamiltonian times the change in the time parameter at each endpoint. So, of course, with the Weiss variation, you can even formulate an alternate form of the variational principle. And the idea, well, the statement is that on physical paths, the variation of the action should consist only of boundary contributions or endpoint contributions for arbitrary variations. And it's really the statement, well, the consequence of that is that for arbitrary variations, Q must lie in the kernel of this Euler-Lagrange operator. So once you have this form of the variation, you have this quantity, the Hamiltonian. Once you've identified that, then you can get to the Hamiltonian formalism in a very straightforward way. What you do is you identify the degrees of freedom as the quantities that are varied at the endpoints, excluding the time parameter. And then you identify the conjugate momenta as the factors in front of the variations of the Q's. And then, of course, the Hamiltonian is whatever appears in front of the delta T term. And then once you have the Hamiltonian, and assuming that you can rewrite the Hamiltonian in terms of just the P's and the Q's, you can compare the differentials dl and dh, and upon comparing them, you can get Hamilton's equations under the condition that the Euler-Lagrange equations are satisfied. So you can get so that's how you get to the Hamiltonian formalism from the Weiss variation. I guess this argument is you can find it in some standard textbooks, but the thing that the Weiss variation adds to it is that the Legendre transformation just falls out of this procedure of rewriting everything in terms of total changes at the boundary. Huh? I'm not sure. I guess what is meant by virtual displacement, so I can't say. One result that you can get almost immediately is the Hamilton-Jacobi equation. And so what you do is you take the Weiss variation and you evaluate it on solutions of the Euler-Lagrange equations. And when you do that, well, you get rid of this bulk integral, and you just get these boundary or endpoint terms. And then once you have that, you just compare it with the differential for the classical action. To simplify things, I just hold I guess the initial Q and T fixed, And when you do that comparison, you can identify the the momentum equation and the usual Hamilton-Jacobi equation. So it just falls right out. And notice that here you don't even need to invoke canonical transformations. You just get it directly from the action. So that's a very neat result.
That's H2 or minus H2?
Yeah, I think that's minus H2. So occasionally there will be sign errors.
There is no last, no, there is no thing as the last step.
Oh yeah, that was a theorem from my advisor. There's no last typo. Anyway, so another thing that you can get pretty quickly from the Weiss variation is a no-other theorem. And so if your action has a symmetry, then you can write it in terms of some transformation. So symmetry means that the action is invariant under some transformation, which I've written in this form. Eta and tau are the generators of this transformation. And of course, these terms are changes to the q's and the t's, and so we can write them as delta q and delta t. And so when you evaluate the Weiss variation of the action on the solutions, so basically you just take the boundary terms in the Weiss variation, do these replacements, then you just get this expression for the change in the action. And these q's have the explicit expression, p dotted into the generator for the change in q, and h times the time generator, the generator of time translations. And if you demand that the action is invariant under these transformations, then you have the conservation of this quantity qa. And so if you have a symmetry, you get a conserved quantity. So that's a quick way to the no-other theorem. And I guess I mentioned canonical transformations, and this is not so much a way to, I guess, derive. This is not really a derivation of canonical transformations. It's just really an explanation of how they fit in. And so one thing that you might say is that, well, if I add endpoint terms or total derivative terms, I can, I'll change the boundary terms and the variation of the action. And so, what's going on there? And whenever you add a total derivative, effectively what you're doing is you're changing the quantities that you're holding fixed, that you have to hold fixed in the usual variation of the action. And I guess you're also changing the quantities that are varying in the general Weiss variation. And so what you can do is, well, you can just look at the variation of this total derivative, that term that you add. Z, these are auxiliary variables that don't appear in the bulk Lagrangian, so they don't affect the dynamics, or they don't have anything to do directly with the dynamics. And the variation of this has this form. And so you can see from this variation that when you add this total derivative to the action, what you're doing is you're changing essentially the quantities that you have to fix in order to just get the bulk terms. And you can choose this generating functional in such a way to perform canonical transformations. And so you can choose, for instance, this piece to this. You can choose the functional dependence of f on q to cancel out this piece in the original Weiss variation, and then you can you can exchange the q's and p's, and so that's one way. That's one type of a canonical transformation, and in principle you can do all of the other types. So there are four, I guess, in the standard approach to canonical transformations, there are four different types of generating functions that you can choose, and in principle you can do the same with these generating functions. equations here. So that's how you would treat a canonical transformations within this formalism. Another, I guess, neat result that you can get is that you can get the Ostrogradsky Hamiltonian for higher derivative actions in a relatively straightforward way. So I guess the equations here are a bit more complicated, and that's because I'm not trying to hide anything, or I'm hiding less here. So here you have this higher derivative of Lagrangian, and when you perform the variation, this is what you get. So you get higher derivative equations, and this boundary term is written in terms of these quantities that are defined here. And so these QMs are defined in terms of the time derivatives of Q, and so they're treated effectively as additional degrees of freedom in your system. These conjugate momenta, which you identify as the quantities that appear in front of these delta Qs, these are defined in terms of this derivative of Lagrangian. And so this is sort of a shorthand for, I guess, the derivative of the Lagrangian with respect to these arguments where you insert the higher derivatives. So of course, the end result is that when you collect all of your terms, you get the Ostrogradsky Hamiltonian, which has this form, but this Q dot you can rewrite in terms of the Q's with lower M's, and so these are effectively your degrees of freedom, and of course you can infer the standard result, which is that generically your Hamiltonian will contain terms that are linear in the momenta, and if you don't have any constraint that restricts the range of your momenta, your Hamiltonian is unbounded below, which is problematic because, well, if your Hamiltonian can be arbitrarily negative, you can pull as much energy out of your system as you like, and so there's an instability there, which is referred to as Ostrogradsky instability. So anyway, that's so the Weiss variation is nice because it provides a straightforward way to get there. So I will tell you now about a really cute result, and this is a quick way of deriving the Schrodinger equation from the path interval. I've seen the derivation done the other way in some textbooks, but it's actually quite hard to find it. Or at least a few years ago, it was quite hard to find the derivation going the other way. I did find it in, I guess, these two sets of lecture notes. And so the idea here is you write down your probability amplitude. So these are essentially the boundary conditions that you're placing on your path. And this here is an integral over all functions for Q of t in some appropriate function space. And what you're integrating is this phase. And what you can do with this probability amplitude is you can construct a wave function by just, I guess, integrating over the initial states, and using the Ehrenfest theorem, which is something that you can show by assuming that the measure is invariant under redefinitions in Q. If you use that, you can get rid of the bulk terms in the variation of that wave function. And when you do that, all you're left with is the path interval of the boundary contributions. So when you do the variation of S, basically what comes out is just these boundary contributions. And since these are quantities that are since these are quantities that are specified externally, so they don't really they aren't really within the functional interval, you can factor them out, and you get this expression here. And if you compare this with the differential of the wave function, what you get are definitions for the momentum, and Hamiltonian operators. And of course, what the momentum operator does is it creates a factor of the momentum within the functional interval, and of course the I guess the Q operator is just something that you can pull right into the functional interval, mainly because we're writing this wave function in the basis of the Q's, and so really you're just pulling the boundary values of the Q's through the functional interval. So in principle, you can just you can construct your Hamiltonian operator in this way, with just this definition for the momentum operator, and this I guess the loose definition for the Q operator that I just described. And so of course this is the Schrodinger equation, the time-dependent Schrodinger equation, and yeah, so the Weiss variation provides a very a relatively quick and cute way of deriving it. Of course, this is all formal because I haven't really defined this precisely. I'm just making some assumptions about its properties. So anyway, so that concludes the first part of the talk, which is really an advertisement for this formalism. Now I will talk about the Weiss variation in classical field theory of gravity. Maybe before I move on, maybe I should stop and ask if there's any questions. Right, if not, I'll continue. So in a classical field theory, you can write your action in this form. So this is some Lagrangian density. This is a measure which is, I guess, defined as your coordinate interval. And the Lagrangian density here, I'm assuming to be a function of the fields, the derivatives of the fields, and I guess implicitly, I'm also assuming it's a function of the coordinates as well. This action is defined over some domain U, and the general variation of this action is it takes this form, and so I guess the first piece, this is just the field equations, and this quantity here, this is I guess you can say it's a covariant, in quotes, generalization of the conjugate momentum, sometimes called the Pauli momentum. And this last piece can be interpreted as the Lagrangian times the area swept out by this displacement vector x delta x mu. And so this displacement vector, this infinitesimal displacement vector, I guess is the difference between the boundary and the displaced boundary and the undisplaced boundary. And so when you contract that into the surface element, that gives you the infinitesimal volume swept out by the boundary displacement. So how do we get this expression into the Weiss form? Well, what we do is we define this infinitesimal displacement vector in terms of some vector field times some parameter, which, well, I've suggestively called delta t. And the total change in the field can then be written as, well, the variation of the field evaluated on the undisplaced boundary plus the Lie derivative of the field with respect to this generating vector field, and times the change in this parameter t. And with this expression in hand, you can write the Weiss you can obtain the Weiss variation for a field action, which has this form. So this quantity here is the canonical energy momentum tensor. And this extra piece is, I guess, something that I'm calling a Bell-Infante-Rosenfeld term, because it because when you work it out, it actually gives you contributions that have the form of Belinfante-Rosenfeld corrections, which are the corrections that are needed to symmetrize the canonical energy momentum tensor. So that's what that term gives you. Now for gravity, for gravity, I guess you pretty much can just turn the crank and you get this result here. So this is the usual bulk term that you get from varying the Einstein-Hilbert action, which is up here, and the boundary term that you get is it's proportional to the total chain in the connection coefficient, and of course, I guess from this expression here, what you have while getting this result is somewhere in there is the Lie derivative of the connection coefficient, and the Lie derivative of the connection coefficient, it gives you a Ricci tensor contribution, which combines with the Ricci scalar piece to give you an Einstein tensor. So that's where that comes from. And of course, one thing that you also get, which partly comes from the Lie derivative of the connection coefficient, is this no other comarker. I guess this is also the thing that's used to obtain quantities like the Wald entropy. And actually, what's neat about this current is that this is identically divergence free, and so you can actually get rid of this this current on manifolds that are, I guess, topologically trivial. So that term is not particularly worrisome. You can get rid of it in some contexts. So anyway, that's the variation of the Einstein-Hilbert action, the Weiss variation of the Einstein and Hilbert action, and it's pretty much more or less what you would expect it to be, if you had to guess from the outset. Yeah.
conservation TV. Conservation can how much the conservation
I guess, yeah, I guess you can. Yeah, so I guess you can if you assume the appropriate symmetry. Yeah, I guess in the Minkowski background, you could get the conservation of beta mu nu. Yeah, but yeah, I guess in general relativity, I do also get, or at least in later you'll see, I also get something like a theta for GR, but and you do get a conservation law there, but there are a lot of caveats to that, and of course the conservation law actually it follows from some identity, but anyway I'll get to that in a few more slides. So so I guess in my dissertation work, what I did was I obtained the Weiss variation for non-null boundaries, and so what the action that I consider is the Einstein-Hilbert action plus this boundary term, the Gibbons-Hawking-York term, and when I form the variation of this action, this is what I get for the boundary terms. Now these quantities are all defined with respect to a 3+1 type decomposition. So this gamma is the projection operator onto the boundary surface. This P is defined in terms of the extrinsic curvatures. And either space-like or time-like.
But before you were doing no?
Before this is this is in general. So actually back then I didn't really get it in this form because I was making assumptions about the properties of boundaries. So this one it was actually derived more recently, yeah, when I first did the Weiss variation, this was the result that I got, and
Sorry, I don't understand, but before you have a boundary, right? You don't have boundary there.
no, in both cases I have boundaries.
So before you which kind of boundary?
This here, I don't make any assumptions about the properties of boundary. This is something that works for an
So that's
arbitrary
general.
event. This is general.
Now we are going to see what happens if you.
Yeah. Well, I guess what I'm doing here, maybe I should have put the slide before, but what I'm doing here is I'm sort of telling you what happens if you assume that the boundary is either space-like or time-like. And again, you get something that's exactly what you would expect, which I guess is nice, but it was a little disappointing because I was hoping to get something interesting, and I got, well, exactly what you expect. This here is the momentum constraint. This is the Hamiltonian constraint, which are both projections of the Einstein tensor. So that's how this result here is related to the previous one, just getting different projections of the Einstein tensor. And of course, in vacuum VR, both of these things vanish. So in a sense, if you just do, I guess, a normal thing, what you get is that the thing that corresponds to the canonical energy momentum tensor for gravity vanishes in a vacuum. Now, more recently, I found a result that is interesting because what you get is ultimately something like an energy momentum, a canonical energy momentum tensor for gravity that does not vanish, which is a surprising result. And perhaps I should minimize this. So what happens? So what you do here is you rewrite the gravitational action in a different way. And so what you do first is you define this quantity, which is the difference between two connections or two Christoffel symbols, one for some reference geometry that doesn't appear in the bulk action, and one for the physical geometry. And of course, the difference between two connections is a tensor, and from that you can construct tensorial quantities. So here, this is just some contractions of this difference, W, and from there you can construct a total divergence. And so physically or dynamically, nothing particularly strange is being done. You're just adding a boundary. That's all you're doing here. Now, when you do the Weiss variation of this action, this is what you get. So you get your usual bulk term. You get something that is, I guess, proportional to the metric. So here, this is the metric can be interpreted as your degrees of freedom for the system, and then you get a bunch of additional terms. This quantity sigma is proportional to terms that are dependent on the anti-symmetrized part of your reference connection. So if you assume that your reference connection is torsion-free, then you can get rid of the sigmas. This is I guess it can be interpreted as a spin contribution to the variation. But it's something that you can get rid of for certain choices of the reference connection. And this quantity theta is a generalization of the Einstein pseudotensor. So the Einstein pseudotensor is what you get if you forget about covariance and you just say, I'm going to treat this as just an ordinary field theory. I'm going to treat GR as an ordinary field theory and just blindly calculate the canonical energy momentum tensor for GR. And this quantity here, it can be shown to be a generalization of the brute force non-tensorial canonical energy momentum tensor, canonical energy moment pseudotensor. So yeah, when I did this derivation, I was quite excited, and then after digging, I found out that Linden, Dull, Katz, and Bichuk had done this back in 1995. Though they didn't do it with the Weiss variation, they obtained it in a different way. But the Weiss variation provides you with a really nice way of getting to that result. So if you have a flat reference connection, so it's a reference connection that's compatible with the Minkowski metric, what you can do is you can choose a vector field that is covariantly constant. And if you make that choice, then your Weiss variation simplifies greatly. And so really all I've done is I've just chosen the reference connection. I haven't said anything about the bulk dynamics. There's no restriction there. And there's a nice identity that's actually derived in these papers, which you can use to show that this quantity, which is the canonical energy momentum tensor for GR, and the Einstein tensor, that quantity is conserved with respect to this reference connection. And so, of course, the first thing that I guess reflexively popped into my mind is, well, does this define a local gravitational energy momentum? And so after my craziness subsided, I realized, well, it's not really the case, because the problem with this the problem with this approach is that a lot of the issues that pseudo-tensorial issues that you encounter when just doing the brute force calculation, well, they go away in some sense because you end up with tensorial quantities. The problem is all of those ambiguities actually are shifted into the choice of your reference. And you might think that, well, maybe you can just choose. I mean, your reference is really, in some sense, a choice of what you consider to be the vacuum. The problem is that even if you choose, let's say, Minkowski space to be your vacuum, there is a lot of ambiguity there, because even if you say, well, the geometry has to be flat, then what you have to do next is you have to choose coordinates for that flat geometry, and that is ambiguous. And so that's so as a result, this thing that you would like to be the energy momentum tensor for gravity, well, that is still ambiguous. It's just that it's hidden. It's tensorial, so it's tensorial, but you still need to choose coordinates for your reference. And of course, there's also this argument that, well, non-trivial local gravitational energy must be at odds with the equivalence principle, because I guess you can always transform into a freely falling frame, and I guess locally you don't see a gravitational field there. So anyway, those are some issues. I've studied this explicitly for Schwarzschild and various coordinate choices, and I either get trivial or pathological results. There's one choice of harmonic coordinates which looks good, but there are other harmonic coordinate choices which are really bad. So anyway, that's the state of affairs. I guess one thing that is kind of neat, I guess another cute result is you can derive for quantum GR, you can derive an Einstein-Schrodinger equation. So you're basically following the same derivation. as the Schrodinger equation for the path interval, except this time with gravity. And it looks like you get this nice Schrodinger equation for GR. So you have some Hamiltonian operator acting on your amplitude, and this Hamiltonian operator, which does not necessarily have to be zero, can give you a time evolution of sorts. And if you're familiar with the 3+1 formulation or the canonical approach to quantum gravity, you might recognize that, well, you might think that this solves the problem of time, because well, the problem of time is that you have, since the Hamiltonian density vanishes, you have this Wheeler-DeWitt equation, which says naively that there's no time evolution. Of course, again, the problem is that this Hamiltonian is ambiguous. You have to choose your coordinates for the vacuum state that you're using for your reference geometry. So you still have that ambiguity there. And the problem is that there's no obvious coordinate condition available. It would have been nice if harmonic coordinates worked, but it didn't. But it might still be useful as a tool in some contexts, and maybe in perturbation theory. Huh?
You also have time.
In which one?
Your formulation.
In this formulation, you have time. The problem is the H is ambiguous, and so yeah. So I guess that's the issue. It's still sort of an open issue. I think there might be ways of making progress on it, but I probably should wrap up soon. So anyway, I guess that is where things stand with the GR. But recently, I've been interested in applying this to modified gravity theories. And so, of course, one of the selling points is that you can get a Hamiltonian for field theory without a 3+1 split. And so it'd be nice to try this on a theory in which it's hard to do this. And of course, the problem is there are too many theories to choose from, as some of you might know. But there is one theory that I think is promising. So this is a theory that one of my colleagues, Shinji Mukoyama, came up with maybe about 10 years ago, and I'm actually surprised it hasn't gotten that much attention. And the idea is you formulate your theory on a Euclidean signature Riemannian manifold, and you include higher curvature or higher derivative terms in your action, and you construct it in such a way that at low energies you have a theory in which you have an effective metric which has a Lorentzian signature. So at high energies, your geometry is described by a Riemannian metric, but then at low energies you get this effective Lorentzian metric. So it's a really neat idea, and what makes it really interesting is that it's renormalizable, and it can avoid the Ostrogrodski instability, which is the issue that plagues a higher derivative theories. And it does that by demanding that the action be a positive definite or bounded below. So this is a potential quantum gravity candidate. Of course, one thing that you might expect is that since you have this effective metric, you might expect singularities at points where the metric becomes degenerate, or effectively when you get a signature change. But I don't see that in the cosmological equations of motion that I get from this theory. So that's something that's a bit puzzling to me. But there's not much more I can do with the cosmological equation of motions at the moment, because they're very complicated, and to do a nice, I guess, to set it up in the form of a simple dynamical system, I would like to have a Hamiltonian.
Just for the background to cosmos, just a homogeneous. I should go for one thing.
Yeah. This is just. I'm just looking at the background. I'm not even. Yeah. The background is complicated enough. Yeah. Yeah. So I guess the way that I'm constructing the model, it's sort of, it doesn't, I guess, have an initial singularity. I'm trying to construct it so that at least in the high curvature regime, there's no initial singularity. So you get something that mimics like a no boundary type of proposal. So at early times you have the Euclidean geometry, and then at late times you have a Lorentzian. So that's the model that I'm trying to investigate with this theory. So anyway, that's where I'm going with this. That's what I plan to do for the next couple of months in Japan, where I will be for the remainder of the year. And so I guess I'll end with that. So here's a summary of an executive summary of my talk, and I'll take your questions.
Thanks very much, Justin, for keeping the time so well. And so, what other questions do we have? Well, it was perfectly explained then. So just for me, because I mean, just naively speaking, because it's something that that comes before I do my T+1 numerical things. In which way could I also make some benefit from this type of developments? Can you think of any way? Could I also use this in order to derive any models?
So I guess what this will be useful for. So if you want, for instance, to do a numerical simulation of a modified gravity theory, of a very complicated one. I guess the Hamiltonian formulation would be a useful first step. And of course, you have to show that the resulting equations are well posed, and that the resulting numerics are stable. But this will provide a first step towards doing those types of simulations. And in fact, that's what I'm hoping to do in this in the simple cosmological model for that complicated theory. So yeah, that's one potential use for it.
Why don't you apply your equation, some model? Cosmological model.
So I guess you can. It's just I guess it's just a question of finding an appropriate choice for this I guess this vacuum state. So I guess if you're so I guess you could choose, for instance, your vacuum state to be some flat geometry or de Sitter or something like that. I think it's possible to do that. Yeah. Well, I guess, but I guess
that's what people do with
yeah.
Relativity.
Yeah. So I guess you can do the Friedman, Robertson, Walker, but I guess the question is, what reference geometry do you choose? So you have your physical geometry, which are evolving, but then that equation is really only well defined if you have some reference geometry to construct. Yeah, you could. Yeah. Yeah. So in principle, yeah.
Robertson, Walker,
Yeah. So in principle, yeah, I think you could do this. You can apply this to I guess the mini superspace type models, and yeah, it might avoid some of the difficulties that arose in I guess earlier attempts to study like Hamiltonian cosmology back in like the 70s. I remember, yeah, one of my PhD advisors, a colleague, you might know him, Michael Ryan. At one point he got fed up with the difficulties. I think he didn't give up entirely, but at one point he announced that Hamiltonian cosmology is dead.
Well, he has a book on that.
Yeah.
Famous book.
I don't know if he wrote that book before or after that paper when he made that statement. Yeah, this might be a useful alternative approach.
Other questions?
So when you do the variation, first you show the general result for any boundary without, like, regardless if it is null timeline for space like, and then the one that is space like boundary. And in the space like one, the boundary term is just the sort of Gauss-Kudati minority equation, right?
Yeah.
So
So this is they're just projections of the Einstein.
but why in the general case you didn't obtain something like this? I mean, naively, I would assume that if you get like the projected equations of a space like boundary, well, you would obtain the same for a timeline for a space like boundary. I mean, here, if you specify your boundary to say timeline, would you obtain also like the Gauss-Kudati minority equations kind of projected on a timeline boundary, or not?
Yeah, I think you'll get the projections, the same types of projections for a time-like boundary. I mean, there are factors of negative signs that you have to account for, but yeah, I guess if you look at what's happening here, so one of the indices of the Einstein tensor gets projected onto the hypersurface, and then I guess another one gets projected onto the no, actually, this one gets projected onto the normal to the hypersurface. And so I guess if you choose your normal and your I guess your generating vector appropriate, then you just get the G00 component. So really you're getting the same result here. It's just that this is the 3+1 version of that.
More questions? And then maybe I can ask another one. Just again, this is not my expertise at all, but you mentioned that this theory you were looking forward to trying, like to testing, the one that advising in Koyama, has these advantages. What makes it different compared to others in which you can like get rid of these Ostrogotski?
So I guess the main difference, so the closest theory would be the Rojava-Lipschitz theory. I guess the main difference I would say is that this theory, which so the action is here, you can write it in a covariant way. Whereas at least the formulations of the Rojava-Lipschitz theory require a 3+1 split, and then I guess it takes advantage of the well, it includes quadratic terms in the spatial curvatures, but I don't know. I prefer personally. I prefer to have something that's that avoids a 3+1 split as much as possible.
Okay, thank you. Let's say last call for questions. No, then let's thank our speaker then.
If you enjoyed the video, like and subscribe.